Hello ladies and gentlemen, my name is Volker Thome. I'm head of the Department Inorganic Materials and Recycling at the Fraunhofer Institute for Building Physics, IBP in Germany. And today I'd like to show you a highly innovative recycling technique for waste concrete. In the previous videos in this modulus about Lighthouse project in RAJKOT, you've already learned a lot about the monolithic concrete construction method in general and how it is applied in RAJKOT. We discussed already how we could improve different aspects of the building construction, like for example the energy efficiency, durability, or also the comfort in the building. Now in the last video of this module we will focus on future development potentials, especially regarding the use of waste concrete. A high potential lies in the recycling of waste concrete. I will show you a method which is able to disintegrate composite materials like waste concrete into their single compounds by applying ultra-short electrical discharges. So why do we even bother with recycling of waste concrete? And where is the problem in the recycling of waste concrete? First of all, we face economic problems. Maybe you've heard that there is a lack of resources for building sand worldwide. Annually, humans need 50 billion tons of building sand for the construction industry. 50 billion tons of sand, we could build a wall with a width of 30 meters and a height of 30 meters around the equator with this volume. So you can imagine this is a very huge volume, and therefore we need techniques to get back sand out of the waste concrete. On the other hand, there are also social problems. The cement industry produces 2.8 billion tons of CO2 annually. Therefore, we need solutions to reduce the CO2 emissions in the cement industry. There is another technical problem. If you crush waste concrete by mechanical methods, you only make small pieces out of a big one. But you are not able to separate the concrete into sand, gravel, and into cement stone. If you use these so-called secondary aggregates for fresh concrete, you have to face several disadvantages. By applying mechanical methods to induce microcracks in the gravel and in the sand. This means they possess a lower mechanical strength than the original ones. As the cement stone is still attached to the gravel, you have a higher water demand for your new formulation. And all in all, it's very difficult to work with this fresh concrete. That's why you need also organic additives to enable a good workability. So you see that we would need a selective separation instead of just crushing of these waste concrete samples. And therefore I'd like to show you now the technique of the so-called electrodynamic fragmentation or pulse power processing method. What are the basics of this technique and how does it work? First of all, we place our solid, in our case a piece of waste concrete, underwater between two electrodes and apply a very strong electrical field to it. We apply about a voltage of 200,000 volts. At the beginning of this process, so-called streamers, these are ultra-short electrical discharges, run through the composite along phase boundaries, and therefore the material gets mechanically very weakened. The first streamer, which reaches the counter electrode, leads to the generation of a plasma channel. In this plasma channel, pressures are generated up to 10 gigapascal. That's similar to a TNT explosion. This causes the material to explode along the phase boundaries. Finally, we can really disintegrate the material into its components and the binder matrix. It sounds as if you need lots of energy for this technique, but the fact is the time of one pulse is only 120 nanoseconds, and we need to process 1 ton of concrete, only 2.3 kilowatt hours per tons. This is in the range of a mechanical processing. In this video you see the result after applying this pulse power processing method on waste concrete. On the left hand side you see a piece of waste concrete, and on the right hand side the products after fragmentation. You can see that you can separate the gravel from the waste concrete. We get a fraction back which is bigger than 4 millimeters, and we get a mixture of sand and cement stone, and finally a fine fraction with a particle size of 63 microns. Besides this, we get also the steel and the reinforcement back out of the waste concrete. The fine fractions are quite special, as they contain so-called secondary calcite. Secondary calcite is formed in the process underwater by absorbing CO2 from the atmosphere. And this is an ideal raw material to produce new cement while simultaneously reducing the CO2 emissions during the cement production. So there's one major difference. By all mechanical methods, you have to overcome the compressive strength to disintegrate a material, and by the fragmentation technique you only have to overcome the tensile strength, which in the case of concrete it's 10 times lower than the compressive strength. So this means this plasma channel expands very quickly and generates a shock wave which runs from the inner side to the outside of the material. So we tear the concrete apart and we do not press it until it's disintegrated. And we can also use steel fiber containing concrete, which is usually a problem. Either you destroy your mill or you destroy the steel fibers. And we're always happy if we have steel fibers in the concrete, because the discharges, they will find every single steel fiber and just remove the surrounding matrix. In general, we can say the more harder a material, the easier it is to process it with the electrodynamic fragmentation technique. So we've started with waste concrete already many years ago, and then we also checked a similar material like refractory concrete. This material is a fire-proofed concrete which is used in thermal processes, for example for steel production or cement production, to avoid the contact between the melt and the oven. It's a kind of concrete, but only with a different kind of cement and different kind of aggregates, but we obtained the similar results. We could easily separate the gravel from the cement stone. Another interesting material are ashes from municipal incineration plants. So they can be obtained by burning household waste. Usually people try to recover the iron metals, and it's difficult to recover also the non-iron metals like aluminum and copper, because these particles are covered with a siliceous layer, which causes difficulties in recovering non-iron metals with eddy current techniques. After fragmentation, we can remove this siliceous layer, and we can obtain a very colorful mixture of particles, and then we can identify the 5 main ingredients: iron metals, non-iron metals like aluminum and copper, glass fraction, refractory fraction, and a so-called melting product fraction. And the mixture will be sieved at 2 millimeters and then can easily be sorted by various techniques like magnetic separator or electro-optical sorting techniques. Another example is, for example, masonry, composite between bricks and gypsum. And this is now very easy to separate. Only after 5 pulses we can really remove the gypsum completely from the brick surfaces. So our exploitation plan is to implement such electrodynamic fragmentation plants in ready-mix concrete plants, with the idea that construction companies or single customers can bring their waste concrete directly to the ready-mix concrete plant, so they don't need to bring it to landfill sites, so they can save landfill fees and we can save also landfill volumes. And ready-mix concrete plant can on-site produce sand and gravel for producing fresh concrete and also final fraction for the cement plant. This means customers can save landfill fees, the ready-mix concrete plant can save costs for raw materials and transport costs, and the fine fractions can be used as a secondary raw material for cement production. They contain especially a so-called secondary calcite, which is produced during the fragmentation process in the process water. So this means the process water absorbs CO2 from the atmosphere, which leads to a precipitation of calcite. And if we use this so-called secondary calcite for cement production, we can reduce the CO2 emissions for cement production by 2/3, which is a large volume, and there's also the greatest potential for using this secondary calcite in the future. This means we can establish a so-called CO2 cycle for cement production and really tackle the problem of the huge CO2 emissions in cement production in the future.